So let's develop some ideas behind doing double integrals in polar coordinates. Now, in an earlier section, we learned how to describe the regions in our double integrals that were referred to as type 1 and type 2. I refer to these as vertically simple and horizontally simple. A type 1 region, which is vertically simple, simply means that you can take a vertical rectangle, that's easy to remember, and the top will always be on one function and the bottom on another. And the double integral for that would begin with dy. The limits would be the two functions of x. In a type 2 region, which is horizontally simple, we think of putting horizontal rectangles, and all of the rectangles go from some function on the left to some function on the right. The integral would be set up with the dx first, and then the two functions of y would be the limits on the integral. Now, if you remember from Calculus 2, when we talked about polar coordinates, when you're trying to describe regions in polar coordinates, you can't use rectangles where you've got length and width of rectangles. Instead, we have to set up sectors of circles that we can use. So we're going to divide this region into sectors of circles. And here's a representative sector. Now, I've got all the things labeled. You can pause and look at that if you like, but what we're going to do in the next few slides is develop the ideas behind the area of this region. So we're going to approximate this sector with a trapezoid, and here's the description of a trapezoid. The area of the trapezoid is given as 1/2 the sum of the two bases times the height. So let's see how that works out with our sector that we've got labeled like this. Okay, so to find the length of an arc, we can take the radius times the angle subtended by that arc. For example, here is a arc at the bottom of this, which, as you can see, is like the B1 in the trapezoid. And so that's equal to the radius, and that would be, of course, this distance, okay, which you can see is given as this, times the angle, and that would be our angle. So here's our expression for B1. We can do the same thing for the arc at the other end. Okay, that would be the distance from the origin times the angle, which is the same as it was in the beginning. Now, substituting the B1 and the B2 that we just found into the area formula, here's our B1 and B2. Now, the H is the distance from there to there, which you can see is our delta R. So we'll simplify this sum. And a little bit more, 1/2 times 2. And so there is the area of each of those individual sectors. in terms of the radius of each times the changes delta r and delta theta. So then we need to take the area of each sector and add those up for all of the r's and all of the thetas. So we need to do the double integral with r going from the beginning and ending values of r and theta going from the beginning and ending values of theta as determined by the region being described. Notice, however, the significant part of this is there's an r that appears in this formula. When we set up regions in polar coordinates to do double integrals, there is this r that appears as part of the theory in the double integrals. So let's work this example so you can see how this plays out. We're trying to do the integral of 3x over the region described here. Now let's draw a graph of this region. We've got a graph where we have r's going from 1 to 2 and thetas going from 0 to pi. Now that is going to be the circular shaped region that you see here, with r's going from 1 to 2 and thetas going from 0 to pi. Now when we set up the integral for this, notice we'll have an r dr d theta. That's just part of describing the region in polar coordinates. So the r's are going from 1 to 2, thetas are going from 0 to pi. Now in your Newton homework, this is referred to as a polar rectangular region. Notice the limits on r are two constants and the limits on theta are two constants, similar to what we had in rectangular coordinates when we were describing a rectangle. I guess you could say this disc looking thing is what rectangles look like in polar coordinates. However, this is the setup on the integral. We still have to convert the integrand 3x so that it's compatible with polar coordinates. That means converting 3x into polar coordinates. So we place the x with our cosine theta, and there's our setup on the integral. Now we'll simplify that. Now let me point out that we could use one of the properties that we learned earlier that says if you've got a function of r and theta multiplied together, you could split this into two integrals and multiply them. However, I'm going to go ahead and do this the old-fashioned way, which is simply do the integral of the inside. So we're doing the integral with respect to r. Now that means we'll leave the cosine theta alone and do the power rule on 3r squared, which would be 3r cubed divided by 3, or just r cubed. Then we'll substitute the 2 and the 1 and subtract. Then we need to integrate that with respect to theta from 0 to pi. Now again, I'll go through that quickly because that's not the intent of this particular lesson. So let's try another one. We need to do this integral. Again, the key is describing the region as we see it here. So the unit circle looks like this, circle with a radius of 1. And again, we want to use polar coordinates. So we'll set up our integral with an r dr d theta. And we want r to go from 0 to 1, and we want theta to go from 0 to 2 pi. So again, this is referred to as a polar rectangular region in your textbook. However, the integrand, 1 minus x squared minus y squared, also needs to be converted. We can rewrite this as 1 minus, and then parentheses, x squared plus y squared. We can replace x squared plus y squared with r squared, and that would be our integrand. A little bit of simplifying, and again, we could use that property, which I'm going to show you this time, and do two integrals. Now again, since our integrand is a function of r times a function of theta, we can split this into an integral d theta and dr, two separate integrals. That was the last property of double integrals that we looked at in an earlier section. So anyway, this is what we come out with. So as a final example, we want to take a look at this integral. And again, we want to begin by describing the region that's bounded by the polar axis and the upper half of this cardioid. So here is a graph of the cardioid. The polar axis, remember, is the one that comes from the origin and goes out to the right. And so bounded by the polar axis and the upper half of the cardioid would be this shaded region. So remember, our integral is going to contain an r and then the dr d theta. So r in this case is going to be going from 0 to the cardioid, which is 1 plus cosine theta. And then the thetas that represent the top half of the circle. Now you could experiment with this on your calculator to see what values of theta give me the upper half of that cardioid. But that's going to be the values between 0 and pi. So the r squared sine theta is already in polar coordinates, and we end up with this integral. Now again, we could use that final property because we have a function of r and a function of theta, only the problem here is we do not have constants. So again, we can't use that final property unless those are constants. So that means we do it the old-fashioned way. The innermost integral, substitute, then the outer integral,